result. Actually, we did not use we did not have used computer algebra for that result. That's very easy to find out that in a mnemonic case an is equal to 1. That's very simple. But what we really want is Pn and Cn. These are more complicated. And here you are, Pn and Cn are rational functions that turn out to be found here.
And Lesky found them by paper and pencil?
And Lesky found them by paper and pencil.
Wow.
That's it, yeah. Okay, and I didn't want to do that.
So,
yeah, Lesky did it by paper and pencil. That's a good question, but it was clear. I told you he never looked at computer algebra system in his life. So that's what we have. Now you see A and B and C, and we can do the same for the other. And actually, if we do all the three, we get, again, more information. In my 98 paper, we have solved some problems for orthogonal polynomials by this approach. But now we want to continue. Now I want to show you that these things can be looked at from a different point of view. Namely, now assume that instead of a differential equation, a recurrence equation is given. So, if a recurrence equation is given, then we can use these formulas that we have and try to find whether there is a differential equation of the type we have seen that is compatible with it. And then it turns out we have to solve a nonlinear system. By the way, that's quite easy to understand. The Chebyshev polynomials of first and second kind, for example, satisfy the same recurrence, but have different differential equations. So there must be sometimes several solutions here. And that's exactly what we do. Here is a question. Here's a recurrence equation. There's even a parameter alpha involved here. We would like to find out whether there are classical, continuous, orthogonal polynomial families that satisfy this recurrence. And then we look for the same question for the discrete case as well. Let's do it with Maple now. So here is the result. I load some packages that we need here. Here is the recurrence equation that we have looked at. And now it is very simple. This is the command RE to DE. We use a recurrence equation and make a differential equation out of it if possible. And this is the classical case. And look for the result. You see that's very simple. It's not a very complicated system. Actually, one can show this is a quadratic system, so therefore you do not really need Gröbler bases or something like this. It turns out that, first of all, there is only a solution if alpha is equal 1/4. No other choice. This parameter alpha must be 1/4. Otherwise, no classical systems are solution. But if alpha is equal 1/4, then there are some solutions. There's exactly one solution. With this row, for example, this is the density with living in this interval, for example. So it's not 0 infinity, it's now minus and 1/2 infinity. And that comes from this factor sigma here. And since it is first order, we know that's the Laguerre case. So we see from this immediately, this recurrence can only have Laguerre polynomial solutions that are shifted, translated somehow, and no other classical ones. But now discrete ones could be valid, and indeed, again, we will find some solutions. Here is the row that is attached to it. Here are the sigmas and taus, and it turns out the sigma has first order, so cannot be the Hahn case, and it turns out this is the Meixner and Kraft-Schuh case. So what we find is this solution. This is done by computer algebra only. You don't need to do these computations by your own. Actually, that's pretty complicated to do that now yourself, although in principle it can be done. So now Doran's algorithm, of course, plays an important role in our work with orthogonal polynomials. He designed an algorithm to compute recurrence equations for this type of sums. You have a summand which depends on two variables, should be a hypergeometric term with respect to both. Then what you get after summing with respect to all k, a function of n, and he gives a recurrence equation as output for Sn. Actually, it's holonomic. That means it's in general, it's a homogeneous linear recurrence equation with polynomial coefficients, and these are of highest importance in this field. And here's Dor. At that time, he had a different T-shirt, you see. Now we look for the formula that you see here, and not for the formula that you saw here. So, namely, his sum is the sum k over all integers. It's n choose k squared, if I remember correctly. It's 3n plus k choose k, or what do we have? Nothing. And he points that this should be 3n.
Should be 2n.
2n choose n squared.
And here we have n.
And what is incorrect?
2n.
2n. Okay.
Oh, n plus
okay.
k.
Plus
n plus k. n plus k plus k.
To the left.
Yes. Could be. But I want to put it like this because that's what I have done in Maple now. So I don't want to do differently from my Maple. So let's do this with Maple. First of all, here is the input. Binomial n k squared plus times binomial 3n plus k 2n. And this is our left-hand summand. We sum with respect to k, and we would like to find a formula using Sn. If we do this, then closed form will find you a formula. If first order recurrence is the output of his algorithm. Here is the formula, and now I can close this again so you see better. This formula doesn't look as nice as the binomial coefficient, but that's the typical output. It's a hypergeometric term, so it is written in terms of Pochhammer's. That's what is normal. But of course, since we know already the result, we can also divide by the right-hand side, namely by binomial 3n squared, and do the same approach again, and what the output is then is clearly 1. That's his algorithm. Very simple. So now, what type of hypergeometric function is related to this question? If we look for this summand here, what we have is a hypergeometric function which is a 1, 2, 3, f2. So this is related to the Hahn polynomials, actually, with the 1 here. So it's not a Hahn polynomial since there is no minus x somewhere here, but it is related to Hahn polynomials, this term, in a way. So let's look for something else. Namely, we could also do the following thing. Assume you have not fnk, but fxk. X is now a continuous variable, or say a variable with which you can differentiate. Then what you get finally is s of x here. And if this is a hypergeometric term with respect to k and a hyperexponential term with respect to x, that means the logarithmic derivative is a rational function. That's quite a similar thing. Then you can find differential equations with this approach. We will do that very soon. And then finally, if you have two functions that satisfy a differential equation of this type, and you add these functions or multiply these, then you get again such a holonomic function. The same with the recurrence equations. So this is an algebra, and you can do this algebraic relations with it. And I just want to show you some of these things here. First of all, that's the Laguerre term. That's the summand of the Laguerre series that you saw already. Minus 1 to the k, binomial n plus alpha n minus k. That's the n plus alpha n minus, choose n minus k term, divided by k factorial x to the k. So that was exactly the summand of the Laguerre polynomial that we saw before. If we enter this here and use your algorithm, some recursion is your algorithm, then you get this recurrence equation. So that's the recurrence equation for the Laguerre, very simply derived. And all these computations typically are very fast, really amazing. Or else we use a similar thing. Instead of some recursion, we use some differential equation, because here is also an x involved, and everything is fine. That's hypergeometric term with respect to k, hyperexponential with respect to x. So you can get this differential equation by your algorithm applied in this way. And of course, that was the differential equation we started with. That was exactly the differential equation for the Laguerres with the x in front of the second derivative that we have now found again, starting from the hypergeometric representation. So we have now done a back and forth algorithmic approach. Or else, you can also find a recurrence equation with respect to this parameter alpha. No problem if you like. You get this here. It's just a change of the name that you have entered here. Or else, if you have the Laguerre differential equation that you saw before, second order, and you plug it in here twice, then you get the square of the Laguerre polynomials and you find a differential equation for it. Here is the differential equation for the square of the Laguerre polynomials. You can also do Laguerre n times Laguerre m and multiply it, and I don't know. You can do all these algebraic things that you want. Or else, here is finally the difference ln plus 1 alpha x minus ln alpha x, and we write this down and get a recurrence equation. And if you look at this, it looks as if you have seen that before. It looks exactly the same like the Laguerre recurrence. And it is, indeed, there is a relation that this difference is a Laguerre again, which can also be seen by the differential equation. It's, of course, the differential equation of our type, Laguerre, the second order times x, linear times derivative, and so on. So this is exactly valid. So this is what we got, all these results here. So now I would like to come to something that I did almost at the same time, a little later than you had your algorithm invented. I invented the following thing. You start with, say, this guy here and get some result for that here. Assuming you do differential equations for such sums. So if you have this right inside, then Zylberger's approach gives some results for the left. I do the opposite thing. I start here and assume this f is a function, an analytic function or something, is some function term given. And what we would like to find is this on the right-hand side. So the AK, a formula for the AK. And this is the so-called FPS algorithm that I designed, and this is implemented in Maple. Everybody can use it as convert from a power series. It's embedded, and this was written, actually the code was written by Dominic Grunz and myself, and finally it was embedded in Maple by Thorsten.
So you don't have to load any package?
No, this is embedded.
Convert is a famous command.
Yeah. This is embedded. It's not so easy to embed something in Maple, but this is embedded. So this is the FPS algorithm. I just show you some results. So if you have, for example, the sine function, and I'm lazy, I don't write formal power series, I write just FPS, which works too. So if you have the sine function and you would like to see this as a power series, then you just say convert sine x to a formal power series, and here you go. If the variable is k is free, then k is used, because that's a very nice variable. So now assume what happens if there is a second variable involved, sine time of x plus y. If you use this here, then the power series is written in two parts, namely that's the even part with the even powers of x, and that's the odd part with the odd powers of x, because the recurrence equation happens to be of the form ak plus 1 divided by ak plus 2 divided by ak is a rational function. Then you have to do that, or you can do that, and that's all done automatically. And actually, what is this, what you see here?
Addition formula.
That's the addition formula, exactly. You can see the sine y, and here's the sine, the cosine x. And so that's the addition formula. That's and you can also do that now. We apply the FPS now on this term here. If we do that, then what we get is clearly double sums. So now, but still, that's the addition formula in a summation writing. Or else,
is this what really came out of the computer, or did you do some cleaning up of the results first?
And I mean, let's do that afterwards. I have my time. actually, of course, you had to do some cleaning. It is quite clear that in some cases you will not easily get factorials. So you have to find a way to get factorials if you like them and so on. So actually Maple likes the gamma function best. It doesn't write things in factorial form. So that's why we had to do some cleaning. You're absolutely right. So now, assume we convert the Laguerre polynomial to Farmer power series. This works as well. You get now again the Laguerre power series, of course, with the Polynomial symbols because they disappear here in a natural way. So this package deals with all kinds of orthogonal polynomials and special functions as well that can be dealt with here. So now I show you how this works internally. That's the nice thing with Maple. If you have the info level variable and increase it to 3 or 5, then most authors, or say some authors, give you some internals. And that's very, very nice. You can use it for many commands in Maple. And here is what we did. It shows you exactly what we do. For the sine function, we try to find a differential equation of order 1. We are not successful. We try to find a differential equation of order 2. We are successful. Here you go. And it could be any holonomic differential equation, not just one with constant coefficients. Now, we look for the coefficients, so we transfer this differential equation to a holonomic recurrence equation for the coefficients. Here you go. So ak plus 1 is a multiple of ak. That's why you had to look for two specific parts, namely the even and the odd parts, and finally you get the result. So this is exactly what internally is done, and that's it. So I come to the final part here. I want to show you some website that was originally designed by Tom Kornwinder and his group and is now in my hands in Kassel. So KOP is Computer Algebra and Orthogonal Polynomials. That's so to say my abbreviation. It's a web tool for calculating formulas for orthogonal polynomials online. Everything is done in Kassel at a computer and using Maple and my codes. You see the word Eskew-Wilson scheme. We will look at that later. This implementation was originally done by René Swartau, but then it was kind of old-fashioned, and we had to redo that and did that recently, namely 2012. And here is the site. Let's look for this site here. So if you start this page, you will see there is some information about what is used and what can be done. But the main thing is there are two menu items, namely orthogonal polynomials and pure orthogonal polynomials. We did not see the right-hand terms already, but we saw a lot of orthogonal polynomials. And here you see again, many of these names are now known to you. Hermite, Charlier, Laguerre, Krafft-Schuck, Meister, Jacobi, Hahn. These are the polynomial systems that you saw already, and that are exactly those that are the classical ones. All the other ones that here are on this list are of the Wilson type, and these are a little more complicated. We'll soon see how these show up, but I just would like to show you what happens if we look for Laguerre now. Laguerre were the polynomials we looked at already, and here you see what happens is, first of all, you get the definitions as a sum and as a hypergeometric function, so you have all these definitions there, and this was done with Maple now. Differential equation, recurrence equation was computed with Maple in Kassel at this moment. And if you like, you can do some changes here. You can, instead of parameter n, you can call this parameter m. Yeah, that's not such a big deal. But you could easily also ask for x squared here, for example, instead of x. And if you do this and submit it, then the program will try to solve this. And then you will see, indeed, there is a differential equation, but this time an x squared is appearing. This is no longer orthogonal, of course, and there's also a recurrence and so on. You can compute all these things online as you wish. So now let's look for the second group, pure orthogonal polynomials. And we didn't have the time to look at all these today. There is a big list of orthogonal systems here. And these are the polynomials of the Q-Eskew-Wilson scheme and the Q-Hahn scheme. So we'll just have to have a short time to introduce these to you, how they came.
Minus 30 seconds left.
Yeah.
Okay.
Okay, minus 30. So if you use, instead of the discrete measure, the integers in this form, Q2 power integer, then you get the Hahn tableau. These are Q polynomials. If you have a quadratic lattice, you have the Wilsons. and if you Q quadratic classes, you have the SQ-Wilson tableau, and all of these polynomials can be dealt with in a practically similar way. And actually, this is still ongoing research. Not all these 7 different definitions can be handled for all these systems. That's what I wanted to say.
Well, yes, I have a question.